Alright, so this lesson is on how to add vectors without using a protractor and a ruler, which we used in our previous lesson when we were doing the graphical method. So the method we're going to do here is what is expected from here on, basically using geometry and trigonometry to solve for the sum or difference between two or more vectors. So let's start off with a simple problem. We have a airplane that is moving north at a certain speed, and it's being blown towards the east with another speed. And we want to know what the magnitude and direction of the plane's speed is. And so we want to understand this is a relative velocity problem, or actually a velocity vector problem, where we have to add the wind speed to the airplane speed, but understanding that the east and the north, they're not along the same line, so we can't call one positive or negative, nor can we just say 200 plus 50 is 250. So the method we're going to use, like I said, is going to use geometry and trigonometry. So there's basically 4 steps. First, we want to sketch our velocity vector. So if you have a straight edge handy, that would be nice. I'm going to just try to use a Smart notebook. So I'm going to represent the north vector like this. So I'm going to draw a vector to represent the plane's velocity in the north direction. And then I'm going to do the same thing in the east direction, which I'm going to call actually to the right. Okay, so I'm going to do it like that. I like to do east to the right, and it doesn't really matter where I put the vectors, but it helps if I place them tip to tail. So if I look at this one, the east one, I'm just going to move it down a little bit so I have it tip to tail with my north vector. Okay, so how you draw your vectors initially actually can make a big difference as to how easy it is for you to do it. So I'm going to call this the 200, and I'm not going to put the units just because it's easier, and I'm going to call this the 50. Okay, so notice that it did not have to be to scale. Alright, you only draw vectors to scale when you're going to do the graphical method, protractor and a ruler. Alright, so now we have 2 vectors. The next thing is to sketch the resultant. Alright, so the resultant is the beginning of one vector. It doesn't matter which one. So in this case it's the eastward vector, and I'm going to go to the end of the northward vector. And again, it'd be nice if I had a straight line, but it's not critical here, and I'm going to put an arrow there just to indicate that that is my resultant R. Alright, and so many of you have noticed us already that I can find the value of R because we have a right triangle, and R is the hypotenuse of the triangle. So we can find the magnitude of R by applying Pythagorean theorem. The vector A squared plus the vector B squared equals the resultant squared. And then the next part we have to do is a trigonometry. So let's do the work off in the bottom here. Okay, I trust you know how to do the Pythagorean theorem, but let's work it out anyway. So we're basically saying R squared equals 200 squared plus 50 squared, and so you add the squares and then take the square root. So the square root of that whole thing is going to be essentially 210 kilometers per hour. Okay, and that's rounded off. So essentially what's going to happen is, even though the plane wants to head due north, because of that side wind, if it points due north, it's actually going to be moving north and east. So if this was its starting point and its destination was way off here somewhere in the distance, it would miss it by quite a bit by the time it got that far. And so any pilot worth his salt knows this, and they make adjustments accordingly. So if I'm going to be a pilot and I have to aim my plane more along this line, I need to know what angle to apply it. So we need to know what angle this is. And this is the hard part for students. Not so much because of trig, they're just not sure where to put the angle. So again, R is our resultant. So I want to know what angle it is pointing in terms of north, south, east, and west. So I need to find an angle on my triangle, and we always measure the angle from the beginning of the vector, just like we had before. So I want to find that theta right there. So at this point, we recognize we have 3 sides. We have the adjacent side here, the opposite side, and the hypotenuse. But since we know the adjacent and the hypotenuse fairly exactly, and this was calculated, let's base it on the adjacent hypotenuse. So we're going to use SOHCAHTOA, and hopefully recognize that the trig function that matters for this is, I'd say, tan of theta, tan of the angle I'm looking for, equals opposite over adjacent. Okay, 200 divided by 50, and that would give me 4. Now that's not my answer. This is not 4 degrees. Now I got to do the inverse tangent of that, or actually negative inverse tangent of 4, is going to give me some angle. And if you punch it in your calculator, make sure you're in degree mode. That's important, because if you're coming from math, you'll probably be in radian mode. This gives us 14 degrees. Okay, so this angle is 14 degrees, but we're not quite done. So if I want to get the full answer, what is the magnitude of the resultant velocity, what I would say is, oops, I'm not sure when that came up. All right, let's try that again. We would say that the velocity is 210 kilometer per hour. Now I got to reference the direction. So we can't just say 14 degrees. We got to say, is it north, south, east, west? So this is going back to what we learned before. So our reference line down here is the easterly, and we're above the easterly. In other words, we're north of east. So I'm sorry, let me erase that. I forgot the 14 degrees part. So we would say 210 kilometers per hour at 14 degrees north of east. So we can't use a protractor here because we haven't drawn a scale. We have to do trigonometry. Again, the trig part isn't hard. You just got to recognize where to draw your theta, and it's always at the beginning. And this angle is referenced to the east. Okay, so let's look at a similar problem just involving more than two vectors. So let's say I've got a rhino that's on the loose and it's walking in a city, and it goes 4 city blocks west, then south, then west again, and then it stops. And we want to find a displacement. So what we want to do, like before, we want to sketch the vectors and kind of anticipate where we're going to end up. So we're going to be heading west, which is left, and then down. So I'm going to start over on the right. So I'm going to sketch a 4 vector. I'm not even worried about how straight it is. Then I'm going to turn south, and I'm going to call it 5. And then we're going another 8 to the west. And I'm just putting them tip to tail. So I want to find the resultant of that. And the resultant of that would be the beginning of my first vector to the end of my second vector. Okay, actually I will draw a line here. And, oops, I don't know what happened there. Let's try that again. Okay, so there is my R. Unfortunately, I don't have it in a different color. Maybe I can do it. No, let's leave it like that. Okay. So how would we find the value of that? Well, if we look closely, we can make a right triangle that looks like this. Here's one leg, here is the other leg. And so I know that this leg is a southerly component, so that's just 5. And the long leg is nothing more than the sum of the 4 and the 8, so that's 12. So we can say the displacement, okay, we'll call displacement R, is equal to the square root of 5 squared plus 12 squared, which, if you work it out, gives you 13 blocks. All right, and then we need the angle. Okay, so the angle again is measured from the beginning of the vector, the resultant vector, so it's this angle right there. And we can see that this vector is pointed in the southwest direction. But our reference vector here, this vertical one, is in the south, so this is going to be west of south. Now we just have to find that angle, so I'd say the tan of theta equals, all right, opposite over adjacent, 12 over 5. And if I solve for theta, again, make sure you're in degree mode, we'll get 67 degrees. All right, which kind of makes sense. This looks like a fairly large angle. So I say 13 blocks at 67 degrees. And again, we're west of south. Okay, so that's the essence of adding 2 or more vectors using right angle trigonometry. Now we want to reverse this. Okay, so for example, what we want to do now is what we call breaking vectors into components. So if suppose you have a treasure map and you want to find something, and you are starting at a certain location. Okay, so we're on some island, we're starting here on the island, and you have a compass, and you know that whatever you're looking for is 200 meters 37 degrees south of west from a rock. So if this is where I'm starting and my treasure chest is somewhere over here, okay, we want to know, and this is from here to here, the direct route, the displacement is 200 meters. And we are south of west, so I'm going to draw a west line, and we're going to go south of that. That's 37 degrees. Sorry, that's so sloppy. The question is, how far west and how far south do we have to go to reach there? So what we want to basically do is take this awful looking vector, maybe I should try to make it a little straighter. Okay, there's our vector. And I want to break it up into components. In other words, understanding that in order to have gotten from the beginning to the end, I had to move, or I could have moved, south and then west. So what we do is we draw two components. One of those components is heading west, and I just go as far as I need to until I'm directly over my end of my resultant. And then I turn and headed south, and I have a south component. So here's my south, and here's my west. And we want to know, of the 200, how much is west and how much is south. So we can do simple trig. Okay, so the west component, we got to recognize from SOHCAHTOA, is the adjacent side. And so the trig function that makes sense for adjacent is cosine. So I'd say the cosine of 37 equals my adjacent side, which is the west vector, divided by hypotenuse, which is 200. And so if I do 200 times the cosine of 37, okay, we will get 160 meters. I'll leave it to solve for W, do 200 cosine 37. And then the south component, which is the opposite side of that triangle, goes with the trig function sine. So I'd say the sine of 37 equals W divided by 200. And if I work that out, and you should work it out yourself, you will get 120 meters. And so what we're basically saying is, if this is 160 and this is 120, then the vector sum of 160 and 120 is 200. Now, we're not going to just add them and say 280. We got to do Pythagorean theorem, and if you worked it out, you'll see that it's 200. Okay, so the last problem we want to try to do is adding three vectors that are tip to tail. Okay, and then we're going to use this by the component method. So let's say I have the following three vectors. I have one vector that's this way, directly east, another one that is south of east, so here is my 40 degrees, that's going to be important. And then I have another vector C that is west of south. So I've drawn that reference for you, that's 20 degrees. Now I want to know what the vector sum of all three of these vectors are. Alright, so this is a fairly involved problem, so pay close attention. What we want to do is we want to sketch basically the components of each vector, add all the verticals, add all the horizontals, and then recombine them into one vector. Okay, so that's what this table is for. So let's do the first one. Sketch the horizontal and vertical components of each vector. So I go up to vector A, it's all horizontal. So there's no vertical, so I don't have to do anything with that. In vector B, we can see that it's down and to the right. So what I would basically do is I would draw a rightward component, and I'm going to call a downward component. And I'm going to call this BX, and this is BY. Alright, X and Y components. And then for this one, I would go down, and I got to put an arrow, and I go to the left. And so this is CY, and that's CX. Okay, Y for vertical, X for horizontal. So now let's use trig to find each component. Alright, so A, horizontal component, it's all horizontal, so this would be 10 meters per second, and 0 for the vertical. For the B, now I'm going to the left, so if I do that, I see that I'm going to call left to the right, that's positive, so I use my trig. The X component is the adjacent, so I'd say basically B is going to be equal to 10, right, the magnitude of the vector, times the cosine of 40. When you work it out in your calculator, that's 7.6.